I'm a hydrogeologist. My motto in life is think out of the box. My name, Marcel. My experience, groundwater and soil contaminations. I'm the creator of Geo RGB, a channel of geographic information systems, GIS, geology, hydrogeology, and contamination. The purpose, the objective, the goal, the intention, the target, the desire. Share my experience and acknowledge to create points of discussion. The Geo RGB community. Promote the use of free and open source software. A free digital society. Provide technical advice to environmental companies. An opportunity for professional growth.
Hello guys and welcome back to my channel. In this occasion I'm presenting the Geostatistical Analysis course related to the creation of groundwater flow maps with Kriging Interpolation. We are going to be working with R and Rstudio for the geostatistical analysis and graph design, and with Quantum GIS for the final map edition. We are going to compare the results we get with the Geostatistical Analyst extension of ArcGIS to see how we can get the same results. However, ArcGIS is a private software, but Rstudio and Quantum GIS are open source and free software. I am going to create a series of video tutorials where you are going to learn how to create a Kriging interpolation successfully. Unfortunately, Kriging interpolation is a kind of black box where most of the people just press the button next without understanding what is the math behind the Kriging method. However, in R, there is no button for next. In these tutorials, I am going to explain with examples, step by step, the spatial analysis methodology, where I'm going to be talking about exploratory data analysis, experimental semi-variogram, model semi-variogram, cross-validation, Kriging interpolation, and also at the end we are going to be working with the map edition with Quantum GIS and also reporting results. This is the 6th video of the Geostatistical Analysis course, and today the main topic is the Residual Semivariogram and also how we can analyze the trend removal. However, at the beginning of the video, we are going to be talking a little bit about how we can calculate the directional semivariogram with ArcMap. Then we are going to do a very extensive analysis about the trend or trend removal. We are going to be talking about the simple line regression and also the multiple line regression. And we are going to create some graphs associated with the residual values. We are going to create a three-dimensional plane associated with the trend, and also we are going to interpolate that surface. Then we are going to create a grid for the interpolation area. At the end of the video, we are going to work with the residual semivariograms, and we are going to plot the cloud, the omnidirectional, the directional, and also we are going to create the variance map for the residuals. Okay, let's go to do it. In the previous video, we manually calculated the semivariance and we plotted the result in a semivariogram cloud. Later, we was talking about the components of a semivariogram: the seal, the range, the nugget, and also the partial seal, and we saw how the nugget effect can impact in our results. Also, we learned how to create a beam to work with the lag distances according to the different beam directions. we created an experimental semi-variogram for 4 different directions. And then we did the variography interpretation in order to identify any anisotropy. At the end, we place a beam on a map to see how it works. Remember that if you missed this video, you can hit the card located at the top right corner of your screen. Today we are going to talk about the trend, or how we can remove the trend from our data. But first, I would like to introduce a little bit more the concept of directional experimental semi-variogram that can be calculated with ArcMap. We was talking about this topic at the previous video, but it was most of the time related with Rstudio. Now let's go to see how we can do that one with ArcMap. Just go to this option, Geostatistical wizard, then select your dataset. In this case, it's going to be this layer here, and for the data field is going to be the groundwater. Then select Kriging, and press the button next. Here we have different kind of Kriging type, but the 2 most popular are the simple one and the ordinary one. And there are other different options that we are not going to talk about it. We are going to use the ordinary one because if you want to use the simple one, what you need is as we are not going to do any kind of transformation, you need the mean value for the parameters you are going to analyze. But what we have is the mean value for our observations. That's 57 observations because we have 57 piezometers. But this mean is not good because what we need is the mean of all the area, not just for our piezometers. For instance, if we are doing a normal score transformation of our data, we are going to assume that the variance for the data is going to be equal to 1. In that case, we can apply the simple Kriging Interpolation, as we know that the variance for all the area is equal to 1. But as I know, in our case, we are not applying any kind of transformation. In that case, we cannot use the simple Kriging Interpolation. The option we can use is the ordinary one. In this case, as I said, we are not going to do any kind of transformation, and we are going to do a trend removal, but at the moment I'm going to process the information without doing any trend, okay, to see how looks like compared with Rstudio. Then ordinary, and we're going to talk about the predictions, okay. Then press next. We have in this screen a lot of parameters, but most of them we know already how they work. The general option here is just to optimize the model. If you want to press this button, you can optimize. Then for the variable, we are working with the semi-variogram, and also you can select the covariance. Then here for the model nugget, you can, if you know the nugget is going to be 0, you can put here false, and then there is no options. But if you want to edit any of these options, you can put here, by default the software is assuming that the nugget is 0.09, but if you want to introduce any value, you can put here false and introduce a value you think is the correct one. Then let's go to leave this one like this at the moment. This one is to modify what kind of mathematical model you want to use, and here you can add the parameters for that mathematical model. Here if you want to do the experimental semi-variogram using anisotropy, then you can select this option and then select what is the mean or range, and also other different parameters. Let's go to leave at the moment like that. And here is for the lag. In our case it's going to be 15 meters, and this one is going to be 30 meters, 30 lags. Just to have here 400 50 meters, that is the total extension of our area. We are going to talk about the mathematical model later in a different video. Then here we have also different options. If you go here to show points, then you can select what points you want. If you want just the semi-variogram cloud, is these red dots, then just select here the bint one, and if you want the experimental ones, just select the averaged. Is this one here. That's the omnidirectional one. If you want to add any specific direction, just go here, show shared direction, and select true. And then here you have your bin with the lag of 15 meters and 30 lags. And also here, I believe you can manipulate the bandwidth and also the tolerance angle. And we know already about these parameters. But as you can see, we cannot see the numbers related what is the tolerance angle or also what is the bandwidth. Then here, if you take from here, then you can manipulate the bin direction. Let's go to add here the all points. That's for the semi-variogram cloud and also for the experimental one with 90 degrees bin direction. This one is for 45, this one is for 90, and this one is around 135. And that's what we calculated with Rstudio here. With 0, 45, 90, and 135. And also we calculated the omnidirectional, it was this one. Also here in ArcMap we have the variography here. And we calculated already with Rstudio. Then I'm going to take the directions, false. And now what we have here is the omnidirectional one, is this one. And the variography we calculated the other day, it was this one. And it's this one here. Now let's go to talk about the trend. The question is why we have to remove the trend of our data. Well, you know, when you apply Kriging Interpolation, Kriging is taking the assumption that the data is stationary. And if you have a trend, then your data is non-stationary. If you want to know more about the term of stationary, you can hit the card located at the top right corner of your screen. That is for video 3 of this course, and we talk about that concept in that video. Then let's go to close this one here, go here, and when you go to do the Kriging interpolation, Kriging, and you press next, then here in this option, just for ordinary one, you can select order of trend removal. Then you have no one, constant, first, second, and third. That's the polynomial ones, first, second, and third. And for the constant is assuming just the trend is constant, right? And if we go to the first one and then press the button next, you are going to see that screen. And that screen provides you the information related with the plane that is going to be removed from our data. You have to understand that this plane is a three-dimensional one. We have X, Y, and each line is representing a specific groundwater elevation. And here we have the parameters that were used to calculate this plane. Then, for example, if we go back and then we select the second order, next, here we are going to have a different plane, but in this case this plane has a curve because it's a second order, and it is the same for a third order. This one is going to be a different plane, but we have now two different curves because of the polynomial of third order. In groundwater, the most common plane that we are going to remove from our data is going to be for a first one, because what you don't want is to overfit the model on your data. I'm going to show you here with a different one. For example, we analyze the terrain in video number 3 of this course, and we get these results. That's for X. For X, the one fits better is the linear one. That's the first order. As you can see, even we cannot see the number, the second order and also the third order, right? Because it's just a linear one. But if we check the other one, that one, it was for groundwater versus coordinates X, and the next one is for groundwater and coordinate Y. Then in this case, we can see that we can fit also a second and also third order of polynomial. But what we don't want is to overfit the polynomial with our data. Let me copy this graph and let's go to talk in a different software. This one here. Because, for example, you can say that the polynomial is doing something like that, and it's going to fit better on our data, right? But that one maybe is going to be a polynomial of order 8, for example, and that's overfit the data. Then for groundwater, we have to assume that the groundwater is moving from the areas of high pressure to areas of low pressure, following the gravity. Then it's going to be, most of the cases, something like that, right? It's going to be a linear plane, you know? That's for 2 dimensions, but you have to understand that we are talking about 3 dimensions. Now let's go to analyze all this data and try to understand all these concepts better. First, we are going to work with a simple linear regression, where we are going to work with groundwater versus coordinate X and also groundwater versus coordinate Y. And then we are going to do the multiple linear regression, where we are going to do the groundwater versus X plus Y together. Then let's go to copy the script here. Then first, let's go to run the attach script. That script is going to help us to just know to explain each time where the data comes from. As we did this script, now they know the X groundwater, it comes from this data over here. Is this one here. Let's run the first one. As you can see, that one is the groundwater elevation. Here is the coordinate X. It's just a scatter plot for groundwater and X. And then the next one is the same for Y. And then we are going to run a Pearson's correlation test to see if the 2 variables are linearly correlated. Then let's go to run this one first for groundwater and X. And what we get here is the correlation is really high, because in this case the maximum it's -1, and if we get -1, we are going to assume that all the dots of our data is going to be on the line. That's perfectly correlated. But that one is -0.8, that it's really good. And then also the p-value, this value over here is smaller than 0.05, and that refutes the null hypothesis that indicates the linear correlation of our data. Then if we run the second one for groundwater and Y, we have also a really high linear correlation that is close to 1. In this case, the maximum is going to be 1 and the minimum is going to be 0. For 0, there is no correlation between the data, and for 1, the correlation is perfect. It means that if we make a regression line, all the dots of our data are going to be on the line. Also, in this case, the p-value is close to 0 and is smaller than 0.05. Again, it refutes the null hypothesis, and this indicates that our data is linearly correlated. Now let's go to create our linear model where groundwater is a dependent variable of x coordinates. Then let's go to run this one. And now let's go to plot the groundwater versus coordinate x, and let's go to do the regression line with this script here. We have the regression line over there. And now let's calculate the residuals. And now let's go to be the residuals. Is this table here? The residuals for x. Okay, residuals for x. And let's go to talk a little bit about these residuals and these values. We are going to have two graphs, this graph, and also we are going to have a graph where we are going to plot the residual value from piezometer 1 to piezometer 57 versus to the coordinates. Is this graph here? And let's go to analyze this data. Then this line is our trend for the x coordinates. And this is our regression line, the parameters for our regression line. Then what we want to do is remove this trend from our data. And that's what we have here. Then let's go to place a line here at 0 to here. Let's go to make this one thick and with blue color. And this line is the same as this one. But here, as we remove all the values here, all the trend, now this line is 0. And these dots are the residual values. Then the residual value is calculated with the perpendicular line for this regression line to the dot over here. Has to be perpendicular. Something like that. Let's go to change the color for a red one. And that's the residual for this value, is this value over here. And that's the residual one. And it's the difference between the plane to this one. And that's the way how we can remove the trend from our data related to the coordinate x. In Rstudio we have similar graph also to analyze. Is just go here and plot the model x, this model. Then go here, select this option here, mark over here with the mouse, and then run. And you are going to have the residuals versus fitted. This graph is a little bit different than the one I showed you, because here we have the residual values and here we have the groundwater. But in the other case, here we have the residual values and here we have the coordinate x. Okay, it's a little bit different. Then here what we want to see in this graph, that we have the data that is split, the half of our data in this side and also the half of our data in this side. And we don't want to see any trend here. I'm going to explain you better now. I'm going to copy this graph and paste. Then what we don't want to see here is something like that our data is, we have to be aware, for example, here about the units. Here is 2 and here is minus 1.5. Even our data is presented like that. The values here are very small. Then it's not indicative of a trend in this case, right? But if the difference between the values is higher, you don't want to see something like that. Okay, but here the difference from here to here is very slow. It's just 1.5. Okay, and that's not bad. Also, what we don't want to see is, for example, that we have here, make this one bigger. For example, the number of dogs here is too much higher than the number of dogs in the other part of the graph. That also is not good. Then also other things we don't want to see is, for example, that we have something like that on the graph, right? Something like that. That it's indicating a clear trend that is doing something like that. Okay, and that's the 3 scenarios I would like to talk about it. In this case, the residuals are good, and we can assume that the data is stationary for the residuals. Also, other important point is that our data has to be normally distributed, right? And that's the next graph. That's the normal QQ that show us how most of the points are on the line, and that indicates that our data is normally distributed. For the next 2 graphs, I'm not going to say anything related with these ones. And let's go to move to the histogram also to see how our data is normally distributed. Then here we have the squeeze to do the analyze for the y coordinate is the same as x, and we are not going to do that one because it's the same information. Then we can conclude that the residual values for groundwater and x are good for the Kriging interpolation because the data is stationary. Now let's go to see a multiple linear regression. Let's go to copy here, paste, and this is a multiple linear regression. Then in this case the model is going to be x plus y. Then here we have 3 dimensions, right? The groundwater is the z, and then we have the x coordinates and y coordinates. Here we have just 2 dimensions, and we was working with the groundwater and x. Then here the model, it's a little bit more complex. Then let's go to run this model. Let's go to see the summary information for this model. And we get here some interesting things. First, the p-value. The p-value is very small, that it's smaller than 0.05, and that indicates that the groundwater elevation, depending on x and y, is linearly correlated. Also for the r squared, it's 0.9, and that indicates that 92% of the groundwater variability can be predicted with this model for the variables x and y. Then it's indicative that the first polynomial model fits really well with our data, because the 92% of our data can be predicted with this model. We have to be aware that it's not the final model, that is not the groundwater flow direction plane, okay? That it's a trend that we want to remove from our data. But even in that it's not the real groundwater flow direction, the plane is really good to predict the groundwater flow direction, okay? In a 92%. That's the point. And that's why we can use a first polynomial to remove the trend from our data. Now let's go to create the residuals. And now let's go to build the residuals. Is this table here? That's for x and y, that's the residuals. And then let's go to plot the histogram to make sure that the data is normally distributed. Okay, it's pretty normal, as you can see here, the bell shape. Now let's go to plot the model. Plot model x and y is this model here. select here and then press intro or enter. And here we have the residuals versus the fit. Even that one, it makes this kind of shape that looks like it's a trend. The values, as I said before, from 0 to 1, it's very low, right? It depends how you make the graph, right? If you make the graph something like that, you are going to see that the points are very close, right? And if you make this one bigger, the sensation is that it is a trend over here. But as I said before, the more or less the half of the dots, it's here at the low part of the graph, and the other half is at the top. And then let's go to see the normal QQplot is this one, and to indicate that our residuals for the X and Y together are pretty normally distributed. And anything else for the next two graphs? Then we can conclude that the model created for the multiple linear regression, where groundwater is a dependable variable of X and Y coordinates, works for remove the trend from our data. And then with this model, the residuals we get are going to be valid for the Kriging interpolation. With this analysis, just for this one, it's good enough, but I decided to do these ones because that one is less complex, and I believe it's easy to understand how the methodology works for calculating the residual values. Now what we are going to see is create this plane in a three-dimensional model. Then let's go to paste here the script. And let's go to run this library. Remember that you have to install the package first. I did already. Then I have to run just the library. Then we are going to compute now the regression model is this one. And we did already because this one is the same as this one here. Now let's go to create the grid where we are going to create the three-dimensional plane. Now let's go to feed the points for the dropping lines to the surface. Let's go to specify what are the variables to create the graph. And now let's go to run this script to create the graph. And this one is our graph, where we have the plane and we have here the residual values is these points over here. As we cannot rotate this graph on the space, what I'm going to do is change here the angle for 45 degrees. And then I'm going to save some images, and then I'm going to pass all the images together, and we are going to see how the plane rotates. Okay, I'm going to export here as an image, and I'm going to save some of the image. This is the final result. Here at the top you are going to see the degrees. I rotated from 0 to 360, making an angle of 45 degrees. As you can see, the plane is not totally complete because the plane goes under this plane over here, the XY plane. Okay, let's go to rotate. Now let's go to back from 360 to 0. Okay, that's it. Now I would like to show you how you can create this plane with Rstudio. It's going to be the same as this one. Let me show you. If you go here, select the data, Kriging, co-Kriging, next, ordinary one, and then if you select here the polynomial for the first order, you are going to get this plane. Then I'm going to show you how you can create this plane using Rstudio. That is going to be very interesting. But in order to create that plane, first we have to define what is going to be the area where we are going to interpolate. Then we have to define an area in our map. Then let's go to do that one in Quantum GIS. I'm going to remove this one, and then we are going to select here a layer, create layer, and it's going to be a new shapefile layer. Select a name. We are going to put here as area to interpolate, save, and then here is going to be a polygon, and this one I believe is good. Let me check first. 4326. I'm going to use the same data as here. That one is 32634. Then we are going to create with the same reference coordinate systems. Then here, okay, the same. Create new layer. Then here, area is going to be a shapefile. Save is going to be a polygon. Then here we have to change for this one here. Okay, and for the rest of the parameters, that's okay. Okay, and now we have the layer here. Press this button to edit the layer, and we are going to create a square. Then it's going to be something. Cancel. Is there something approximately to show you how you can select the area of interpolation? Then select an ID, it's going to be 1, and then we have the area for interpolate. Let's go to make this one transparent. And that's it, apply, okay. Then we are going to interpolate our data in all this area for the groundwater flow direction, and also for the plane that we are going to use to remove the trend in our data. Then if you go here to finish the edition, just save, and then when you go here to properties and then information, you can see here what is the extents, okay, the maximum and minimum values for X and Y. Okay, then you have to use these coordinates to define the extension of your plane. Okay, and that's what I did. Then I'm going to copy and paste the script here. It's going to be over here, paste. And this script is going to be how to create a grid. Then let's go to run these libraries. Then I'm going to transform the coordinates A in spatial points. I believe I did already. Let me check. Formal spatial points. Yeah, it's that one, but I'm going to run anyway. Then we are going to define the extension of our grid. As I said before, you have to use the maximum values for X and also the minimum value for X, and the same for Y, maximum and minimum. That is going to be the extension. Then run this one. Then the next one is going to be how big you want the pixel of your grid. In this case, it's going to be 0.5 by 0.5 meters. That's a very high resolution. Then let's go to run this one. Then we are going to transform the grid in spatial points with this one. That's a lot of things you have to do. It's something that you have to do step by step because there is a lot of information, but if you pay attention, it's not really complicated. Then in order to plot the grid with ggplot, we have to do this transformation, transform the OR grid as a data frame, and I'm going to put a different name. It's going to be that one, grid as a data frame. Then I'm going to run this one, and then we can plot the grid with ggplot. That one is going to take some time because the resolution of our grid is really high. As I said before, is 0.5 by 0.5, and then we are going to have a lot of pixels of information. As you can see, it takes a lot of time here. With this symbol is saying that the software is processing the information. Now I'm going to pass the video faster. This is our grid. The red dots are our piezometers, and all of these squares is 0.5 by 0.5. And then we are going to get a value for the plane we are going to interpolate for each square of 0.5 by 0.5. And also when we do the Kriging interpolation for the final map, we are going to get also information for each of these squares. But as you can see, the density of the squares is really big. Then the resolution of the map is going to be really big. Then with this grid, let's go to interpolate the plane that we are going to remove from our data. I'm going to close this one. I need to grid it, our grid. And now I'm going to paste here the next script. Paste is this one here where we are going to create the plane for the trend removal. Then I'm going to run this one. I'm going to run this together. Then I'm going to define what kind of polynomial we are going to use, as with this equation here. Then I'm going to run the linear regression model as we did previously. Then I'm going to full grid the grid we created. Now I'm going to fix this one. Now I'm going to use the linear regression model to interpolate the surface, the plane. This one. Now let's go to create the map, the surface map. As you can see, this plane is the same that we saw with ArcMap. Then I tried to do the same in order to get the second order polynomial for this one. If you go here, next, ordinary, I try to reproduce for the second order polynomial with this result, but I couldn't do it. I don't know what is the problem or what is wrong. Maybe someone can provide, I don't know, extra information related with this issue. But if we run this one, the second order polynomial with this equation here, and we did the same steps as we did for the first polynomial, we are going to get the next result. So I'm going to show you. Then as you can see here, there is a warning message that it says the prediction from a rank deficient fit may be misleading. Then maybe something that our data it's not good to create a plane of second order for the polynomial. I'm not sure, but the point is I couldn't reproduce the same results as I get in ArcMap. And I'm going to leave that one for the Geo RGB community. Maybe someone can help with that thing, but you know, it's not a big deal, because even I'm not going to use the second order polynomial because I believe it's not the adequate one for removing the trend. I believe the first polynomial is the best, and it's not a big concern for me, and I didn't spend too much time trying to investigate how we can fix this issue, or maybe it's not an issue, and with that data we cannot create a second order polynomial. I'm not sure. Then when I run to create the map, I get the same results as the first order polynomial. There is no difference. It's the same map. Now we can create the semi-variogram with the trend removal. Let's go to paste here the script, and let's go to start to run all these scripts. Okay, that one is removing the trend from the data, and first what we are going to see is the cloud of residuals for a linear trend that is going to be the first order polynomial. Previously we was using a constant trend that it was designated with this equation I'm going to show you. Here at the directional semi-variogram, we was using a constant trend for the groundwater, but now we are using a linear trend for the residuals. Okay, this one here. Okay, let's go to run this one. I designate it as a variogram residual cloud. Then we can plot this one. And as you can see now, the points at the semi-variogram cloud looks more randomly as before. You know, for the one that we was using a constant trend, the semi-variogram cloud, it was showing a trend, but it's not this case. Then in order to make a nice graph, we can use QGplot. Let's go to run this script. And here we have the semi-variogram for the residual cloud. The next one is going to be the script in order to calculate the variance for the residual values, because we want to add a red line on the graph to indicate where is the variance of our residual data. Then let's go to run all this one together. And the value for the variance for the residuals is 0.15. Then the next one is how we can create the experimental semi-variogram for the residuals. It's going to be the omnidirectional one. We are going to call this one as a G-trend. Let's go to create the G-stacked object. And now let's go to create the variogram that is going to be this one. Now let's go to plot. And as you can see now, the experimental one doesn't show a trend as it was showing before. Then there is a silt over here that is going to be 0.16. This value here for the variance. Okay, now let's go to make this graph nice with QGplot, and also we are going to add the variance with this red line. That's the variance we calculated. Now let's go to calculate the residual semi-variogram in 4 different directions with azimuth tolerance angle of 22.5, and for these 4 directions with a cutoff of 150 meters and also with a lag of 15 meters. Let's go to plot this one, and the result is this one. Now let's go to make a nice graph with QGplot. is this one. It's not really nice. It's not a kind of 4-direction semi-variogram that you are going to see in a book, but the important thing is the values stabilize at the seal, and we don't have any trend. That's the important thing. Now let's go to the variogram map that is going to help us to identify any anisotropy. And let's go to run all this one together. Is this one, and now let's go to make a nice graph with QGplot. Is this one. We are not going to analyze any anisotropy. We did already at the previous video where our data shows the trend, but we are not going to analyze for the residual values. We are going to use the omnidirectional semi-variogram with the residuals to create our Kriging Interpolation. That is going to be this one over here. We are going to use this semi-variogram to calculate the Kriging Interpolation. This is the end of this video. For the next one, what we are going to see is how we can calculate the mathematical model for our experimental semi-variogram. Thank you very much for watching this video, and see you on the next one.